I am Abhinav Chandrakar, and today we'll be discussing on the contents of the fourth week of this course, techniques of materials characterization. And this week's content was on transmission electron microscopy. Before starting, there were two doubts related to week three assignment. So but since right now not many people have joined, I'll wait till the end and we discuss the week three doubts in the end. Also, in the last week's doubt session, there were there was a doubt regarding relativistic effects and how the wavelength needs to be corrected for relativistic effects if the velocity of electron is too high. So I'll try to elaborate on that a bit in this session so as to clear that doubt. Let's go to the relevant uh, content of week 3. So the doubt last week was regarding at what values of velocity can we expect that the wavelength will change significantly and we'll have to use the relativistic effect instead of using the value which is corrected for the relativistic effect, instead of directly using the wavelength value which we get using the de Broglie equation. So the I had partly explained it last time, but I'll just explain in a bit more detail this time and we'll quickly finish it. So the de Broglie wavelength is given by lambda equal to h by mv, where h is Planck's constant, m is the mass of the body, and v is its velocity. But if v is a significant fraction of c, which is the velocity of light, then there will be due to relativistic effects, there will be a change in the mass of that body, and it will be different from the rest mass. The mass tends to decrease. And here it has been shown that if we apply a voltage of about 100 to 300 kilo electron volt, like if the voltage is 100 to 300 kilovolts, which is typical in case of TEMs, then the kinetic energy of the electron will correspondingly be 100 kilo electron volt to 300 kilo electron volt, and the wavelength from the de Broglie equation will be between 0.0039 nanometer to 0.0022 nanometer. But if it is corrected for the relativistic effects, then there will be a decrease in the wavelength, And in case of the 300 kilovolt applied, the decrease will be by about 10%. So a decrease of, so in this case it's about 10% decrease in the wavelength, which is a significant amount. And the exact formula for calculating the relativistically corrected wavelength is like this. Let's call it lambda star. And we know that if v is quite small, we can neglect this term, the new lambda equation, and we'll get the de Broglie wavelength the term only. But in case v by c is large, for example, so in case v by c is large, let's say approximately 10%, in that case it will be better to incorporate this relativistic effect and use the corrected lambda equation, so that the wavelength that you use for your further analysis is will be able to give you the correct results. Otherwise, many of the calculations you will do with the incorrect lambda will lead to incorrect results. That's why it's important to consider for relativistic effects, especially when you are doing TEM. With that, let's start with session 4. So, as we did last time, we'll firstly recap the week's topics, but this time we'll spend a bit of less time on it. And after that, we'll just so during the recap itself, we'll discuss the doubts related to the lectures, and at the end, we'll solve the assignment for week 4 and some of the doubts pertaining to the assignment of week 3. Here are some small questions I made up based on the content of week 4. After this session, you can try to answer these questions. So, as I said, this week's content is on transmission electron microscopy, and I hope I'm audible. Just if you can write in chat, it will be helpful, whether you can hear me clearly or not. And also, TM is a bit of a complicated topic in terms of it requires some effort to understand it, because there are a few new things that you will be learning. So I hope this session will be helpful for you all for understanding TM, and if there are any doubts, please let me know. Okay, so in the first lecture, Monte Carlo simulation was covered. This was also covered in last week's content, where it was shown how what are some ways in which using which you can understand how the electron beam interacts with your material. So there are some statistical techniques to do it, but there is also this technique called Monte Carlo, which is more popular and useful. So this is more often used for SEM, because there you have thick samples and you have a variety of interactions of the electron beam with the specimen. Maybe I can just go to week 3 and show the relevant part. So here we talked about interaction cross section, then interaction volume, and yeah, here we had Monte Carlo simulation. So here the image was shown, but it was not explained what it is. So let's look at it in the current week's content. Hmm. I won't go line by line as to what was taught, but what Monte Carlo simulation does is it tries to it basically simulates all the possible trajectories that the electron can have once it has encountered the material, and there can be a variety of interactions, both elastic and inelastic, about which I'll talk about in the coming slides. So we want to know because there are lots of interactions that can happen one after the other. The electron can interact with the atoms, then keep going forward and again have some interactions. So to be able to kind of visualize the multiple interactions that happen, we use this kind of a simulation technique. Here, all these thread-like things you can see. For example, the blue ones here. If you just pick one of them, you will see that these are going in. These are kind of like threads which are going in a particular direction, but they are not going straight. So these are nothing but the simulated trajectory of one electron as it is going through the material. And we can see that there are blue and red threads. So the red lines are for the backscattered electrons, the trajectory for those electrons which got backscattered, and the blue ones are for the absorbed ones. And in order to be able to uh, know the approximate volume in which the interaction of the electron with the material happens, there is a metric called KO range, a Kanaya Okayama range, which using this formula for KO range, we can get a radius of the radius of the approximate interaction volume, and this interaction volume depends on many factors. So it depends on the atomic number, the atomic mass of the atoms, Z, which is the atomic number, rho, the density of the material, and the energy of the incident beam. And here we can see the KO range for different elements for range of incident beam energies. And here we can see that for lighter elements, the interaction volume is more. The electron beam can penetrate deeper into the sample. And as the energy of the beam is increased, the kinetic energy of electrons also increases. And that also helps the electron beams to penetrate deeper into the sample before getting totally exhausted and absorbed. And as a result, we get this kind of a trend. Here also we can see some similar simulations where the different interactions and the volumes of interactions are shown. So what are the factors which affect this interaction volume? I just mentioned them in the KO equation. But do the factors affect it in the way that it was shown in the equation? Firstly, look at atomic number. So as the atomic number increases, the nucleus of the atom becomes mm, the charge of the nucleus of the atom increases. And since the interaction of negative electrons with the positive nucleus can lead to Coulombic effects, Coulombic repulsions, as the atomic number will increase, the interaction of the electrons will be much more stronger with the nuclei of the atoms which are there in the material. And as a result, there we can expect that there will be more scattering of electrons. So last time we had talked about mean free path and interaction cross section area. So using those terms also we can understand that if the atomic number is higher, then the electron will be more likely to get scattered by the atom, because the cross section interaction cross section will be higher, and the mean free path as a result will be lower. So it is much more likely that after one scattering event, the electron will again get scattered by another atom that it will encounter. So by this logic, we can understand that atomic increasing atomic number will lead to more scattering. And I think the effect of incident electron beam energy is understandable on the interaction volume. As the kinetic energy increases, the interaction volume will increase, because the penetration of electrons into the material will be higher. It will take more number of scattering events for the electron to lose its energy. Now let's get into core TEM related content. So in the last week, I had covered the basic arrangement of the lens system used in TEM. So what are the components? The electron gun, the condenser lenses, condenser aperture, the specimen. Then we have objective lenses and objective aperture, selected area aperture. Then we have intermediate and projector lens for projecting the image. And finally, we have a fluorescent screen for showing the image. And then we have some detectors which can collect the signal, and which we can later on use to form the image and analyze our specimen. And this is how basically this is the basic arrangement of the different components in a TM machine. Now in case we have scanning coils, we had not discussed this last time, but in case we have scanning coils also being used, then in that case you can, instead of having just one uh, longitudinal beam, you can have a beam that scans in a raster fashion over the surface of the specimen, and using that you can get information related to you can get information of a broader area, as well as some particular information which you cannot get from plain TEM. When I say that it scans in a raster fashion, I just mean that if this is the specimen, then the fine electron beam will start from one point on the specimen, and it will move in a way in this kind of manner. And as it moves over the whole specimen, there will be all the signal that we are collecting will be used to correlate with the position from which it is collected, and from that we'll be able to get an understanding of the characteristics of the of the specimen over the whole of this area. Now that we have understood the arrangement of the components, let's try to understand how the imaging occurs in TM and how we are able to generate contrast, which is the basic requirement when you are doing any kind of imaging or microscopy. So we had discussed about what is contrast when we were studying optical microscopy, which is the most rudimentary and important too at the same time. So it is the oldest and the first microscopy technique that came up, optical microscopy, and many of the principles that are used there are also very much relevant in case of electron microscopy like TEM. So there we have understood what contrast is and how it helps in being able to get distinguish the different features in our images. So in case of TM, we can have two kinds of contrast. One is the phase contrast and one is amplitude contrast. So if there is a change in the amplitude of the electron beam as it goes through the specimen, in case of TM we have a thin specimen, so the electron beam goes through it, and if there is a change in the amplitude of the electrons, then the contrast generated as a result of it is called amplitude contrast. And if there is a change in the phase of the wave, of the electron wave, in that case we call it a phase contrast. So amplitude contrast will be generated because the electrons from the incoming electron beam, as we know, will get scattered by the atoms in the specimen, and those parts of the specimen which will scatter more will lead to a reduction in the will lead to a reduction in the number of electrons which are transmitting through. So lesser number of electrons will transmit through the specimen, amplitude of the electron beam which comes out will be lower, and that will generate a contrast. Similarly, if there's a change in phase when the electrons transmit through, not exactly transmit, but there can be other phenomena also. But when the electrons go through the specimen, if there is a change in phase, then that phase can also lead to a contrast between different regions of the image. So this is a TM micrograph where we can see that there are some black regions, blackish, darkish regions, and some lighter regions. And we can see that this in this way we can have a contrast between different features of the specimen. Here you have gold and titanium oxide. Now that we have some idea of how a contrast can be how the contrast is generated in different imaging modes in TM. So just in the same way as we had multiple modes for optical microscopy. For example, bright field imaging, dark field imaging, fluorescence microscopy, differential interference contrast microscopy, phase contrast microscopy. So all of these different techniques led to receiving different information and different signals by through the different signals about the specimen. And all of these techniques or different modes of optical microscopy had their own benefits. based on the different ways in which they operated. So similarly, TM also has some different modes and variations, and all of them have their own benefits. And based on our requirements, we can, once we have understood these requirements, we can decide what is appropriate for our investigation and for what we want to investigate in our specimen. So the first and the most straightforward mode of imaging is the bright field imaging mode. So here, just like in case of optical microscopy, uh, we uh, allow direct the direct beam of incident electrons to pass through a small aperture, while all the electron beams which have got diffracted and into in different directions, they are blocked by using the this aperture, and as a result the image is formed only using the beams which transmitted directly through without getting scattered. So as a result of this, in the image we'll only see we'll see those regions brighter where there was less scattering of electrons, and those regions where more scattering of electrons occurred. The scattered electron beam will get blocked by the objective aperture, and we'll have a much darker contrast. So when we have a specimen which has different atoms of or different phases of different mass of different atomic masses, so there might be a region which has atoms which of higher mass, while another region might have atoms of lower mass. A contrast in the image, and that kind of contrast is called mass contrast. So as I earlier touched upon, as the atomic number of the atoms increases, the atomic mass will also increase, and it will lead to more of Coulombic interactions of the electron with the atom, which will lead to more likelihood of scattering as well as scattering by larger angles. So if we have atoms of larger mass, we can expect that there will be more scattering, and as a result a contrast will be formed on the image. This is called mass contrast. So in case there are any questions you can ask. And this is our TM image where we have small spheres of micron size, and we can see that as the thickness of the shell is increasing, the spheres are becoming darker and darker. This is because the mass of these spheres has increased, and as a result more of scattering of electrons is taking place, both scattering and absorbing, and because of this we are getting a contrast in the final image. Now, along with the mass of the individual atoms which the material or specimen is made of, the thickness of the specimen will also have a contributing factor on how much of the electron beam is able to transmit through without any scattering, because we know that this scattering is a stochastic event. The higher the thickness will be, the more number of atoms the electron will encounter while it is going through the specimen, and as a result its probability of getting scattered will be higher. So we can say that as the thickness increases, as the thickness changes, that will also generate a contrast in the material, and we can expect that those regions of the specimen which are thicker will scatter electrons more, and as a result will have a darker contrast when you are considering bright field image. Just like in this image, the darker portion is due to the thicker regions of the specimen, while the lighter ones are due to the thinner regions. Even if the all both of these regions are made of the same atom or the same composition. Hello, you have a question? If you have a question, please let me know. I can't hear you. Anyways, you can let me know in the chats if you have a question. I'll continue. So we talked about mass thickness contrast. Both mass and thickness generate a similar kind of contrast, so they have been clubbed together here, and we can use this equation to uh, get a value of the contrast due to mass and thickness. Similarly, as I touched upon earlier, atomic number also has a effect on the scattering of electrons. And this is just another TM image. Heavier atom, gold, is can be seen as these black patches, while while the lighter particles of TiO2, atoms of TiO2, can be seen as a brighter contrast in the background. Also, we can see that there is a darker background on the right upper end. This is because of a change in the thickness of the specimen, or the in case of TM we have very fine, very thin specimen of approximately 50 nanometer thickness. So this is extremely thin, and if there is a change in the thickness in the specimen over different regions, that will also generate a contrast similar to the one here, where you have darker shade here and a lighter shade here. This is just because of the change in the thickness. So also, this image shows that multiple contrast mechanisms can operate simultaneously. So here we can see gold nanoparticles on some capsules. So gold nanoparticles can be seen due to mass contrast, while the capsule um, can also be seen due to its mass contrast. Mm. So previously we discussed about bright field imaging, but we also can do dark field imaging in TEM. In case of bright field imaging, we were keeping the aperture such that the direct beam was allowed to the direct beam uh, or the transmitted beam which came through the specimen was allowed to pass through, while all the scattered beams or the diffracted beams were blocked using the aperture. In case of dark field imaging, just as was the case in optical microscopy, for the dark field imaging, we use the aperture in such a way that the diffracted beam is allowed to pass through and the direct beam gets blocked. So we allow only signal from the diffracted beam, and this is done by keeping an aperture in the objective on the back focal plane of the objective lens. So here we have the back focal plane, and this is the plane where the beam of electrons get focused. That's why it is called back focal plane. And here we can choose some of the diffracted. So here we can choose the diffracted beam while keeping the central beam blocked, and as a result the image we'll get will only be based on the diffracted beam, based on the electron beam which has got diffracted from the specimen. Okay, so there are two arrangements which can be utilized for getting the dark field imaging. So one is this one, where those electron waves which got diffracted by some angle are allowed to pass through by shifting the aperture away from the optic axis. So the aperture was shifted from the optic axis, and as a result, only those electron waves which got diffracted by some angle are able to pass through. And this is called the off-axis dark field imaging. But another way to do dark field imaging is by tilting the incident beam. So instead of having the incident beam which is parallel to the optic axis and perpendicular to the lens, we have a tilted beam. So all the electron waves which got transmitted directly through the specimen will actually not lie directly on the which will not actually be parallel to the optic axis. As a result, even though the aperture is still in the same place as it was in case of bright field imaging, just because you have tilted the incident beam, only those electron waves which got diffracted by some angle and are now parallel to the optic axis will be able to pass through. And this kind of imaging arrangement is called on-axis dark field or centered dark field, which is more common terminology. And there are some benefits of using this kind of arrangement instead of off-axis dark field, because we know that there are aberrations associated with any microscopy, with any imaging. When you are working with lenses, there are always some aberrations, and one of those aberrations is spherical aberration, where the distance of the incoming waves from the optic axis of the lens can lead to different focal points for the different waves, and as a result we get smudging of the mm, or we get smudging of the waves. So we had talked about spherical aberration when discussing both optical microscopy as well as electron microscopy, and there we had understood that if the electrons are away from the optical axis, if the aperture size is large, we'll have more spherical aberration. And in case of off axis dark field, the electrons are much more farther than the optic axis, so the spherical aberration will be more. And but in case of tilted incident beam, the diffracted electrons are almost parallel to the optic axis and closer to the optic axis. As a result, aberrations will be less, and this is why on-axis dark field is preferred when compared to the off-axis dark field. Now, if you have any doubts, you can let me know. So here are some images of some biological specimen which are imaged by both bright and dark field methods. So can you tell which of them is bright field and which is dark field in case of for these images? The left ones are bright field because you have a lighter background, and those features which tend to be thicker or being made of higher mass, they scatter the electrons more, and as a result they are darker. But in the B image, you are only considering those signals which are from diffracted electrons, and since diffraction occurs more due to these bacterial cells rather than from the background, we see these to be much of a lighter contrast compared to the background. So this is the dark field image is typically inverse of the bright field image. If you look at the shades, so brighter regions tend to be darker, and darker to be tend to be brighter. This phenomena of generating a contrast by utilizing the change in the diffract by utilizing the difference in the diffraction of the electron beams by different regions of the specimen is called diffraction contrast. So again, to just reiterate, those regions in the specimen which uh, which will diffract the electrons more, which will have higher interaction with the electrons, will appear lighter in a dark field image because the diffracted electron waves are collected by the detector, while the transmitted ones get blocked by the aperture, and this difference is used to generate the contrast. And this diffraction is associated with uh, some specific crystallographic orientations. So in the crystallographic orientation, in case of metallic specimens or with inorganic materials, we have orientations in which the materials are arranged, in which the atoms are arranged, and that has an effect on the diffraction contrast too. I think we'll cover that in the later slides. Additionally, when you are doing TM, what happens is that there are multiple mechanisms or multiple interactions taking place in the between the specimen and the electrons, and because of this, it can many times become difficult to pinpoint to interpret the images that you get during bright field or dark field imaging, because multiple mechanisms are occurring over the whole of your specimen. So we can have mass contrast as well as Bragg contrast or diffraction contrast happening simultaneously in case of crystalline specimen. Mhm. So here we have in image A, we have a TM micrograph of some region of a specimen, and image B shows the diffraction pattern. So you can see some bright white dots. Lots of white dots were arranged in a particular fashion. So these are the diffracted. These basically represent the diffraction, the planes which are diffracting the electron beam, and they give information related to the crystallography of the specimen, the crystal structure of different regions of the specimen. But if you want to be able to clearly understand the different regions which are on the specimen, it's better to get information only from certain diffracted uh, beams instead of using all the diffracted as well as the transmitted beam. And as a result, we prefer to use apertures, for example objective aperture, to be able to only mm, consider particular transmitted beam or particular diffracted beams and get the images from those only, to be able to better understand the crystal structure of our specimen. So here, when only the central beam, which is the transmitted beam is considered, we get this kind of an image. When one of the diffracted beams is used, we get this image. So this part is having a lighter contrast. So this region is diffracting more. This region is having more diffraction of this particular by this particular diffraction plane. While if you consider this diffraction plane, we get this kind of an image. So this region is diffracting more. Here you in this region you have more diffraction. You have more planes which are causing this diffraction. So in that way we can understand the crystal. We can get crystallographic information of different regions of the specimen by considering different diffracted electron beams. Now there is a which is also important. So HADF stands for high angle annular dark field, and this in simple terms, this just exploits the phenomena of stronger scattering or higher scattering of electrons by atoms which have higher masses. Hmm. Here we have a annulus, which is like a ring, which is at a high angle, quite high angle with respect to the optic axis, and because of this we call it a high angle annular dark field method. And here we do not use TEM, we use STEM, scanning transmission electron microscope. So as I was speaking, we there are some scanning coils which are used to do scanning of the electron beam, and in that case we call it STEM. So in case of HADF, those regions in the specimen which have atoms, which have heavier atoms. As I earlier mentioned, the heavier atoms will have more Coulombic interaction with the incoming electrons, and they will scatter the electrons more. And also, they'll scatter the electrons by much higher angles because the repulsion of the nucleus with the electrons is more. As a result, if we use a detector which is of this kind of a geometry, it's made of a ring which is at a high angle with respect to the optic axis, then we'll collect all the signals from the electrons which have been scattered by high angles, and this is more likely to be due to atoms which have higher masses. And using this method, we are able to detect the composition of different phases in the specimen. For example, in this image, we can see that there are some particles which are overlapping, and due to these being heavier particles, they are causing a dark contrast in the TM image. But if we do HADF imaging of such phases, what we'll see is that these particles will scatter more electrons, and as a result, they because they are scattering more electrons, and the annulus, the detector of this annulus geometry is collecting those electrons, those these particles will have a lighter contrast compared to the background, and it will be much more easier to be able to see these particles which are having higher atomic number elements using HADF compared to using TEM. No. This can also be used to determine the uh, chemical identity of your phases. I have already told what is the major difference in the mm, arrangement of components for STEM and for TEM. So you have these deflection scan coils, and also you have certain extra detectors in case of STEM. So for example, you have a HADF detector. Then some more benefits of STEM is that you can carry out more analytical, you can have more analytical techniques such as Z contrast, angular dark field imaging, spectroscopic techniques such as EDS and EELS, which stands for electron energy loss spectroscopy. So all of these use different phenomena to be able to uh, get spectroscopic, that is chemical composition related information from the specimen. But when you are using STM, you have to adhere to more stricter conditions. So vibrations, vacuum level, the electromagnetic noise around these have to be controlled. Mm. So, so we had discussed about diffraction of electrons by the features in the specimen. But how exactly does diffraction happen? The basic principle is that you have some mm, slits of these kind, and when any wave is incident on it, since these slits have a very small spacing between them, the electrons, the uh, outgoing wave, the outgoing wave will tend to not be just planar. So the because of these slits, the waves which are coming out of the slits will interact with each other, and because of the interaction of all these different outgoing waves, there will be a phenomena of interference, and you'll be able to form a diffraction pattern. I think it is talked about more clearly in the coming slides. So let's go there. But the basic tenet of electron diffraction is that here you need to consider electrons also as a wave along with having a particle nature, because all these effects related to diffraction and interference can only be explained by using the wave nature of the particle, sorry, wave nature of the electrons. So even diffraction is just a scattering phenomena, but because in case of crystalline or semi-crystalline materials, the atoms are arranged in a very periodic manner, the scattering also happens systematically, and because of this systematic scattering, we get some special phenomena such as the so we get such special phenomena such as these diffraction spots, which are very periodic in nature. In case the atoms in the material are very haphazardly arranged, for example in amorphous structures, we do not see this kind of a periodic arrangement of the diffracted spots, and the scattering is more arbitrary in this case. But in case of crystalline materials, as I was saying, the arrangement of the atoms, which are basically the scattering center, or you can uh, make an analogy of these atoms as being like the spacing between the atoms as being like slits. So since these atoms are very, scattering also happens in a very systematic way, and because of this regular arrangement, we have a regular constructive interference of the scattered electrons in certain directions, and thereby diffracted beams are generated. In case you have amorphous samples, we saw that you will have this kind of we'll have this kind of diffraction pattern. There will majorly be one maximum near the uh, there will be one maxima near the center, but in case of uh, crystalline materials, if it is polycrystalline, we can have rings of this sort. Well, if it's a single crystal, then we can see this kind of an arrangement of the diffraction spots, and each spot basically represents a diffraction plane, a plane from which the electron beams are diffracting. And from this diffraction phenomena, there can be two kinds of signals we can get. One is related to the angular distribution of the scattered atoms, and another is related to the intensity after the scattering, a change in intensity during scattering. So both of these signals can give you some information related to the atomic arrangement of the atoms. And based on these factors, we can get a detailed information. We can derive detailed information from the diffraction pattern. So now coming much more into the basics of diffraction, after we have understood the uses of diffraction in TM and how we use it for getting dark field imaging, as well as in case of HADF. Now we'll come to the basics of it, uh, how diffraction occurs, and how what are the factors which can affect the diffraction phenomena. So it was Bragg who first gave the mm, who first showed how diffraction happens, and what all factors it depends on. So if we consider a very simplified model, we have stacks of atomic layers or atomic planes, and then there are incident beam coming on those atomic planes. They are interacting with these planes, which are periodically arranged, and they are getting scattered at certain angles, right? But if the and in case of this, you can consider it to be similar to a reflection. And if the angle is of a certain value, what happens is that the phase difference is such that you get constructive interference. The phase difference is almost equal to the wavelength or a multiple of the wavelength. The path difference is almost equal to the wavelength or a multiple of the wavelength of the incoming wave, and as a result you get constructive interference. So no happens when this kind of a diffraction takes place, and because of this constructive interference we get a diffraction pattern. In case of electrons in TEM, the wavelength is very small, almost 2 picometer or 300 kV electrons, and as a result the angle by which diffraction happens, the diffraction angle to theta, it is very small, and for all practical purposes sin theta can be considered to be equal to theta for electron diffraction. And by using this formula n lambda equal to 2d sin theta, we can tell at what theta values for a particular value of lambda and d we'll get constructive interference. I'll try. Yeah, we are almost coming to the end of the week's content. Have multiple different atomic planes in any crystalline material. we know that all of these planes will cause diffraction with the electron beams, and as a result, you will have multiple diffraction spots coming. So the angle of that the electron beams makes with the atomic planes is important, and that determines whether constructive interference will happen or not, and whether we'll be able to see diffraction patterns for a particular plane or not. So for being able to understand whether with which electron with which atomic planes an electron beam will diffract, we can use this concept of zone axis and zonal planes. So if we assume that the electron beam is traveling along one particular axis, and then or then all the planes which are almost perpendicular or completely perpendicular to this axis. So all the planes which have a normal which is perpendicular to this axis will be able to cause diffraction because the theta values are very small. So if the planes are almost have a normal which is almost perpendicular to the electron beam axis, then we know that it will interact with the planes, it will diffract by some small angle to theta. And so for a particular axis, we can uh, we can try to look at all the planes which will be perpendicular to it, and this collection of planes which are perpendicular to a particular axis are called zonal planes, and that axis is called the zone axis. I hope it is clear. So because electron diffraction involves very small diffraction angles, all the um, planes which tend to be almost parallel to the electron beam, or whose normals are perpendicular to the electron beam, they tend to be able to diffract the electron beam, and as a result, they participate in the diffraction phenomena. Their diffraction spots will be visible in the image. And for if the electron beam is parallel to a particular zone axis, all the zonal planes corresponding to that zone axis will be able to uh, create diffraction spots. And if uv comma w is the zone axis and hkl is zone plane, then uvw axis will be perpendicular to hkl, which is the family of planes. So family of planes can be represented as this. And now we'll come to the last. Here we were considering some electrons as a wave which is interacting with this arrangement of atoms as atomic layers which are periodic and regular. But we can also uh, consider the electron beam to be coming as incoming plane waves, since these are coherent electron waves. And using the Huggian's principle, we can assume the atoms to be like secondary spherical electron wavelets, as the we can assume that the atoms will lead to formation of secondary spherical electron wavelets that will have the same wavelength. But just like a wave forms spherical wavelets when it is just like spherical wavelets are formed on water if there is any disturbance. Here also the primary wave on encountering these atoms will form these spherical wavelets, and when these wavelets interact, we'll observe phenomena which will be similar to constructive interference. Also based on mm, which atoms, or based on the maximas of different atoms which are constructively interfering with each other, we'll we'll be able to get multiple constructive interference based on the different maximas of the secondary wavelets of different atoms which are mm, kind of interfering with each other, or basically they are adding up with each other. Interference is nothing but the adding up of amplitudes. So as a result, we'll have different orders of diffraction based on which maxima is interfering, which maximas are interfering with each other. And from Bragg's equation, we know that n lambda equal to 2d sine theta, and here n lambda is nothing but the path difference between two parallel electron beams, which are getting diffracted from the atomic planes. D is the spacing between the atomic plates, theta is the angle of diffraction, 2d theta, 2d sine theta is the path difference between the diffracted waves. So if we want to, if the d value, the atomic spacing between the planes decreases and the wavelength increases, we'll have an increase in the theta value, angle of diffraction. So this is the basic principle of diffraction, and how atoms in a material, in a crystalline material, can cause diffraction. Using the concept of zone axis, we can understand which all planes will diffract, and using some more other advanced concepts related to reciprocal space, we can also tell if we have this kind of diffraction pattern, which plane do each of these diffraction spots correspond to based on the spacing and the position of all these spots. I think it will be covered in the upcoming lectures. With this, the content for week 4 has been covered. If you have any doubts related to these, you can ask me now. Give me 2 minutes. I'll be back in 2. Hello. Let us continue with discussion on the assignment. There were doubts which came up in the discussion forum related to 2 questions in assignment 3. So let's look at them. One was on question number 2. So it was someone said that they couldn't find the correct answer in all of these options. Actually, I also tried to answer this. Any of you also encountered this problem? And did any of you try to solve assignment 3 question 2? And were you able to get correct answer among these options? Hmm. So, okay, I'll just show. Actually, there is none of these options is correct. The correct answer is something else. I'll just show how it can be solved. So last time I had told the formula for de Broglie wavelength, which can be used to find the wavelength of electron if we know the and kinetic energy of that electron. So if we put in the values in this equation, then we'll have lambda equal to h, which is 6.626 into 10 raised to minus 34 Planck's constant by root into 2 into mass of electron, which is 9.1 into 10 raised to minus 31 kg, into the kinetic energy of the electron, which is equal to charge of electron 1.6 into 10 raised to minus 19 coulombs, into the kilovolts applied. So 10 raised to 3 into 200 into 200 kilovolts. If we solve this, we get the answer to be 2.413 into 10 raised to minus 12, which is equal to 2.4 picometer or 0.00241 nanometer. So this is the correct option, E, option E. Another question asked was question 11, whether a SEM can give chemical composition information or not. Have any of you tried to answer this or know the answer to whether SEM can tell about chemical composition or not? Mhm. Feel free to tell me your thoughts, since I'm also a learner only when it comes to these courses. So feel free to just unmute
Hello.
and tell if you have any thoughts related to this.
So, scanning ultra microscope, so it is basically used for the topography only.
Hmm.
So we
Yes.
don't the outer morphology only we can see through the scanning ultra microscope. So I think
Okay, I see.
option A is
Hmm. So you are correct. The most like common application of a SEM is for getting topographic information. How is the surface of your specimen? Uh,
yes.
so this is a correct answer. But if we try to look at a SEM, what all signals you can get from a typical SEM machine? I think it will be in week three's lecture.
Yes.
Then there are some other signals also apart from the secondary electrons which you get. Mm,
So we can get another information other than the topography.
yeah, we can get information other than the topography too. So can you recall some of the other signals that can come out when the electron interacts with the thick SEM specimen, other than the secondary electrons which get detected? What are some other signals that you can get?
Um, so there are primary electrons and secondary electrons, and
Yes. So this was briefly discussed in the week 3 content. We have the secondary electrons, which gives us the topographic information. Based on how the surface is, if there is an undulation on the surface, so more electrons will be able to come out from that raised undulation. And these secondary electrons come from a very small uh, region, sorry, from almost the surface of the specimen, from a very small thickness of approximately 100 nanometer. So they can give you very precise information about the surface. But in a typical SEM, because you have electron beam of quite high uh, kinetic energy, you also get signals from deeper into the specimen. You can get backscattered electrons. So there are multiple detectors which can detect all of these electrons. So all of these signals. So you can have secondary electrons, backscattered electrons, OJ electrons. These have not been talked about in detail yet, but I think in the upcoming lectures they'll be taught more. Also, we have X-rays coming out. So there is characteristic X-ray, something called cathodoluminescence, and continuous X-rays. Why and how they are generated, this I think will be covered in the future lectures. But just based on seeing what is the information you can gain from each of the signal, you can tell that the backscattered electrons, which are basically electrons which had a Coulombic elastic interaction with the atoms in the specimen. So when the primary electron elastically interacts with the atoms in the specimen, there is a Coulombic interaction due to which there is it is also elastic due to which elastic scattering takes place. So the reason we call it elastic is because there is no change in energy after the scattering takes place. So this is generally seen as some electrons being scattered at very high angles. So angles which are higher than 180 degrees, sorry, which are higher than 90 degrees. So if this is the specimen, if this is the primary electron beam, it can get scattered at angles which are higher than 90 degrees. And also we can have some characteristic X-rays which come out when there is a de-excitation of electrons. So when the primary electron beam interacts with the atoms, the energy of the primary electron beam can be absorbed by the atoms, and this can lead to excitation of electrons from lower shells to higher shells. But when they de-excite, they give characteristic X-rays, and using the information from these, we can we can get some information related to the composition of the specimen, the atoms which make up that specimen. So in this way, the signals other than the secondary electrons can also be used, and these can give you information related to the defects, so as well as the composition of the specimen. I hope now it's more clearer. So this is the reason why SEM is a very versatile tool when it comes to characterization of your material. Based on these different signals, you can get a lot of information related to your material, right? So if this is clear, we'll move on to assignment 4.
So does the chemical composition be obtained from the scanning automation?
Yes, so I was talking about characteristic X-rays. You
Yeah.
remember this now,
Yes.
as well as backscattered electrons. So backscattered
Yes.
electrons are basically electrons which get scattered
Atomic
from directly from the electrons interact directly with the nuclei of the atoms, which
Yeah.
is which. So these nuclei of atoms have a very high charge, but they occupy a very small space in the whole of the specimen, since the atoms are primarily made of electron gases only. Very small region in it is the nucleus. So these backscattered electrons are very rare, but based on this you can tell the atomic number, because this gives you information related to the nuclei of the atoms, right?
Oh yeah.
So you can get an atomic number contrast from this, and using this you
Then we
can
can update the chemical
get
composition.
to know what phases are there. So if different atoms are, so if there are precipitates or inclusion, then you can get that information from these backscattered electrons.
Okay, thank you.
And the characteristic X-rays will give you specific chemical composition related information based on the wavelength of the X-rays which are generated.
Okay.
Uh, okay, so let's go to assignment 4. Since we have almost discussed all the concepts, this should be quite easy for you all now. Let's see if you can answer quickly the first question. Any thoughts on what the answer could be? We'll quickly go through all these questions. Hmm.
45 degree.
45 degree. Okay. So firstly, okay, we were just now talking about elastic scattering, right? Backscattered electrons. So when the scattering is by a very high angle, we call it backscatter because it is going in the direction which is opposite to that of the incoming electrons. But the scattering can also happen at smaller angles. For example, in case of TM, the scattering tends to occur at angles which are very low, usually less than 1 degree. So because these nuclei, there are nuclei have a nuclei occupy a very small space in the material. So these elastic scattering phenomena are rare, and the scattering tends to be by very small angles. So to be able to help you visualize this more, if there is an electron beam coming and this is the nuclei made of neutrons plus protons, if it is head-on colliding, just this is a simplistic view. But if the collision is head-on, you'll expect that the scattering will be at a very high angle, almost backscattering. But if the electron is at a distance, then depending on how far it is from the nuclei, the angle will be much lower, right? This is understandable, right? This is basic Coulombic repulsion. So most of the elastic scattering that will happen, since most electrons will be farther away from the nuclei, most of the scattering will be at very small angles, and the maximum scattering will be at almost 0 degrees. Makes sense? So now you are able to understand why it won't be 45 degree. If you have any doubts, you can let me know. Else you can. It's fine.
Yeah, it's
Okay, so let's now try to answer the second question. Mhm. So, do you all understand elastic and inelastic scattering? We have covered what is elastic scattering, right? So, any thoughts on what the answer could be? Okay, let me answer. So, elastics, I have already told that in case of elastic scattering, there is no change in energy. This is a Coulombic repulsion. So no change in energy occurs, but so the answer to should be quite straightforward. It is inelastic scattering. So what are some ways in which inelastic scattering can happen? This has not been covered in detail, but what could happen is that the incoming electrons, which are coming with a very high energy, might knock off some of the electrons from the atoms that are there in the specimen. So these atoms which get knocked off will have a lower energy compared to the primary beam or the incoming beam, and as a result there will be a loss in energy when this knockoff happens. So these knocked off atoms are actually called secondary electrons. Also what can happen is that there can be some loss in energy of the electron beam when due to the interaction with the other electrons which are in the atom. So because it is encountering these charged electrons around it, when the primary electron beam is going through the specimen, there will be some loss in energy as by formation of some electromagnetic waves such as continuum X-rays or by characteristic X-rays, which happens when electrons get excited, which when the energy of electrons is absorbed and the electrons gets excited, and this excitation can lead to emission of a characteristic X-ray later on. But all of these are inelastic scattering because there is loss in the energy of the primary electron beam, right? So if this is clear, I'll go to the next question. Size of the interaction volume and the penetration depth of the electrons. This was also covered in the recap. If any of you know the answer, just let me know. Hmm. So I think the effect of electron energy will be straightforward. If the electrons are of high energy, they are moving with a higher velocity, they'll be able to penetrate more into the specimen because it will take more number of scattering for the electrons to lose all their energy. So the penetration will be more, right? Also, as the atomic number of material increases, I have told scattering increases. So both of these should have opposite effects on the interaction volume. And the correct answer should be increase and decrease for both of these factors. So A. Now let's come to fourth question. In case of dark field mode of imaging, which of these is true? All these MCQs test the very basic concepts which were taught in the lectures. So it's important that you should be able to answer these if you have gone through the lecture. So here the correct answer will be D, because in case of dark field, here you are saying something, Satish.
No, no. I came for the option C. So
Okay, okay, huh. So if you have any thoughts, you can let me know. It's better to discuss all this because in that way, I'll be able to maybe help you with some confusion you have, and we'll be able to discuss more number of things if it is more interactive. So here, first option is zeroth order beam, but zeroth order basically means that um, zeroth order will not be correct because this I think just refers to the primary. Then direct beam is used for bright field, we know, and for dark field only the diffracted beam is used. The reason for using the diffracted beam I had covered while discussing dark field imaging. So the reason was that when we want to get crystallographic information of the specimen of the different regions of the specimen, we want to choose certain diffracting planes from which we want information, and see which regions of the specimen have more of those diffraction planes. So that's why we use dark field mode of imaging, and the option is D. I hope that these things are clear or somewhat clear to you. Else you should try to go through the lectures, because TM can be a bit difficult to understand initially when it's new to you. So let's go to fifth question. What do you think should be the answer to this? I expect that this should be, you should be able to have some idea of what could be the answer for this question.
Option C.
C. Okay. Yes, the correct option is C. Thick areas will appear darker because of what we call the thickness contrast. So the thicker areas will have more material or more number of atoms that the electron will have to encounter. As a result, there will be more scattering. And in bright field mode, we only allow the transmitted beam to pass through. So as a result, since more scattering is happening in the thicker regions, the transmitted beam will have lower amplitude, and so the thicker regions will appear darker. Intensity of the thicker regions will be lower. Now let's go to sixth question. What do you think will be the answer to this? Hmm. Any any guesses to this? If you, even if you if your guesses are wrong, it's fine. If any guesses, let me know.
Zinc appear darker than the magnesium.
Yeah, Satish, you are right. Zinc will appear dark in case of bright field. Mm, this is due to the atomic number effect or the mass contrast effect. Mm. Now let's go to seventh question. Mm. Mm. You want to guess the answer for 7? Okay, I'll answer it. So TM diffraction contrast. Mm, Diffraction uh, in diffraction contrast, we have a diffraction pattern which gets generated. I showed some of the images of it in the lecture slides. From that, from those images, we can get information related to the atomic planes present in the region of interest, which are leading to the diffraction. So the correct answer is orientation of the crystals, because if there is a single crystal which you are focusing on, like which you are considering for imaging, then based on the orientation of the atomic planes in this crystal, you will get your dark field image, or as well as the diffraction pattern, and from that pattern you can tell how the orientation of the atomic planes is by seeing which planes are diffracting. So I hope that was clear. Now let's go to eighth question about. Any thoughts on this off axis and on axis imaging? If you have any doubts related to any of these, let me know. So, what is firstly off axis and on axis imaging? So, the the optic axis is nothing but the perpendicular direction to the lens system, and this is usually the direction from which the electron beam is coming. So, this could be your aperture and lens system. And if the electron beam is coming along the axis and is and if uh, the diffracted electron beam is so in case diffraction is happening, you get the diffracted beam is not along the axis, it is an angle, so we call it off axis. While if transmission is occurring, or then in that case the beam continues to be parallel to the optic axis, we call it on axis. So even in dark field, so firstly in bright field, the diffracted beam is not considered. It gets blocked by the aperture. So these can't be your answer. In case of dark field, you can have both off axis and on axis. I have explained these in the slides when I was discussing both of these. So the answer will be, for having diffracted beam parallel to optic axis, you will have to the answer will be on axis dark field imaging, because here we use tilted incident electron beam, so that after diffraction the electron beam becomes parallel to the optic axis. So answer is C. Now coming to ninth question, what does HADF give information about? So let's quickly finish these. All these things we have already covered while discussing the lecture slides. So I won't spend much time on this. If you have any doubts, you can let me know. Feel free to guess even if you are not very sure about the answer. So HADF involves. Sorry, can you repeat? Atomic number contrast. Yeah, atomic number contrast is the right answer. Since we have a detector which is at a high angle with respect to the optic axis, and the atomic number of the atoms which uh, cause scattering has a high effect on the angle by which the scattering will occur. So the answer is D, atomic number. Now coming to question 10. Hmm. So this is what is the inherent mechanism for any TEM specimen for having contrast. The answer will be A. This is the most generic option because the contrast can either be due to change in the amplitude of the mm, outgoing electron waves, or it could be due to change in the phase. So change in phase is somewhat connected to diffraction, while all of these are more due to the change in amplitude. So correct answer should be A. Now comes, what is the zone axis for these two zonal planes? Any thoughts on this? What could be the zone axis for these two planes? We know that zone axis is the direction which is perpendicular to the normal of the planes, normals of all the planes. So which of these directions will be perpendicular to these two normal directions? Mhm. So we are almost approaching 2 hours. So I'll try to quickly wrap up. If the planes are HKL and the zone axis is UVW, then UH plus KV, the dot product should be 0, since these two, the plane is parallel to the axis, that is to the zone axis, which means the normal of the plane is perpendicular to it. So dot product should be 0, and the answer should be 200. Coming to the 12th question, the angle between the direct and diffracted beam increases with. If any of you know the answer, you can let me know, and else I'll quickly answer these. So this also I have covered. The Bragg's equation is like this. So based on this equation, which of these do you think the answer might be?
increasing option B.
Option D. You mean option D? Okay, increasing distance and decreasing wavelength.
No, the increasing under term distance, the increasing wavelength.
Option B. Okay. So we want an increase in the angle theta. So we will to have a higher theta, we'll require the wavelength to be higher. But since D is like being multiplied to sine of theta, as theta increases, increase, right? So if we want to, if the value of lambda is constant, so you can say sine theta equal to n lambda by 2d, and if we want to increase sine theta, lambda should increase while d should decrease, right? So answer I think should be decreasing a, right? You understood now?
Ah, yeah.
Oh. If this is clear, we'll go to 13. This is again related to Bragg's equation. Hmm. Here we need to comment on the theta value for these two different diffractions. We know that the difference between electron diffraction and X-ray diffraction is in the wavelengths or the energies of the incoming beam. In case of X-rays, we have a larger wavelength, which is typically in nanometers, but in case of electron diffraction, we have a very small wavelength, which is in picometers or sub angstrom. So since lambda is proportional to sine theta, what should the answer be? For electron diffraction, lambda is lower, so theta also should be lower, right? That's why in case of TM, we get thetas which are approximately 1 degree or less than that. So the correct answer will be smaller. 14 question, KO range. The KO range tells about the approximate radius of the interaction volume. So what factors should it depend on? It will depend on all of these. The answer is D. Last question. So this is also related to the Bragg's equation. If any of you have already solved this assignment, you can tell what is the answer you got. Here we need to calculate the distance between atomic planes. So the D value, D equal to N is equal to 1. This is first order reflection. Lambda by 2 sine theta. Theta is 30 degree. So this will be equal to 4 nanometer divided by 2 into sine 30. So sine 30 degree is 1 by 2. So despacing is equal to 0.154 nanometer, same as the wavelength of the X-ray. With these, the assignment 4 is completed. If you have anything, any doubts or anything you want to share, you can let me know. Else, we'll wrap up with this session. Also, if you have any feedback or any changes you want to suggest on how this session is being conducted, your suggestions are welcome. I hope this format is fine and useful for you.
Yes, it is fine to understand, sir.
It's fine, right? If you think I'm going too fast or too
No,
slow,
no,
or you
no.
can let me know. It's fine. Okay, good to hear. And if you have any doubts, you can keep on posting on the discussion forum. Let's finish this session with this. Thank you, everyone, for joining.
Thank you, sir.